Good evening, sir.
Hi, good evening. Okay, so let's wait few minutes, then we'll start. Okay, just a second. Okay, so let's start. Let me just share my screen. Okay, so today also we'll be solving 4 questions from 2014 paper. Okay, so is my screen visible?
Yes, sir.
Okay. Okay, so this is question number 6 from 2014 paper, and so the question says the molecular partition function for a system in which the energy levels are equispaced by epsilon is, so these are the 4 options given. So we have to find out the molecular partition function for a system of energy levels which are equispaced by epsilon. Okay, so let's first draw the energy levels. Okay, let's say this is epsilon equal to 0, then this is the energy state having energy epsilon, this is 2 epsilon and 3 epsilon, like this. So the difference between the two states is the epsilon unit, so that is E1 minus E0 equal to E2 minus E1, like this. So now we know the partition function. The expression for the partition function is the sum of all possible energy states, like sum of exponential of minus beta of all energy of all possible energy states. So the partition function is denoted by Z. So Z equal to sum of I equal to all possible energy states, then exponential minus beta of EI. So here beta equal to inverse temperature, which is 1 upon kBT. Kb is the Boltzmann constant, and T is the absolute temperature. So this is the expression for our partition function, and now we can put the value of EI here. So it will be sum of, like first term will be e to the power minus beta times E0, so let's say I equal to 0 to n or to infinity, then e to the power minus beta e1 plus e to the power minus beta e2 like this. Okay, now we know all the values of e0, e1, e2. So the first term will be e to the power minus 0. E0 equal to 0, we have assumed that. So e to the power 0 equal to 1 plus then e to the power minus beta epsilon, right? The e1 equal to epsilon, then e to the power minus 2 beta epsilon, e2 equal to 2 epsilon plus exponential minus 3 beta epsilon like this. So from this expression we can let's assume e to the power minus beta epsilon equal to x. So this is 1 plus x square plus x cube like this. It goes on like this. So in short we can write this like I equal to 0 to infinity x to the power I. So this is actually infinite series. So the algebraic expression for this infinite series is 1 divided by 1 minus x, or 1 minus x inverse. So now we can just put the value of x. So 1 divided by 1 minus exponential minus beta epsilon. So the partition function for our molecular partition function for this system having energy states of equispaced energy states of epsilon unit is z equal to 1 upon 1 minus e to the power minus beta epsilon. Okay, so here in this case, in this question, the option D is the right answer. The molecular partition function for a system in which the energy levels are equispaced by epsilon is 1 divided by 1 minus e to the power minus beta epsilon. So you have to just to solve this question, you have to just remember the algebraic expression corresponding to this infinite series, which is 1 plus x square plus x cube. It goes on like this, and so sum over I equal to 0 to infinity x to the power I equal to just 1 minus x inverse. So from this expression you can compute the partition function. Okay, so any doubts from this question?
No, sir.
Okay, so let's just move to the next question. Okay, so this is question number 5 from same paper 2014, and here the question says the value of the magnetic quantum number of a px orbital is. So basically so let's first start some of the basics. So any orbital we can denote as psi, is a wave function psi, and let's say this wave function is a function of 3 variables in polar coordinates r, theta and phi. So this wave function is a function of 3 variables, r which is the radial coordinates, and theta is theta and phi are the angular coordinates. So So if you just draw the space, polar space, let's say this is x, this is y, and this is z. Now for any vector, let's say this is any vector capital R. Now the angle between the z axis and this vector, this angle between the z axis and the R vector is denoted by theta. And if you just take the projection of this vector in the xy plane, so this is actually xy plane. Now if you take the projection of this R vector in the xy plane, so it will look like this. Now the angle between the x-axis and this projected vector is called phi. So basically if you just so this will be equal to r cos theta, because the angle between the z axis and the r vector is theta, so that's why if you take the projection of this r vector onto the z axis, along the z axis, then the vector will be just mod r cos theta, and along x axis it will be r sin theta cos phi, and along y axis it will be r sin theta sin phi. Okay, so now so basically for this wave function, if we can separate this into two terms, a radial part and an angular part, right? So radial part will be a function of just r only, radial coordinate, and the angular part will be function of theta and phi. Now we know there are 4 quantum numbers here. Any orbital, for any orbital we can express any wave function with 4 quantum numbers, like n, l, ml and ms. So n is the principal quantum number, l is the azimuthal quantum number, ml is the magnetic orbital quantum number, and ms is the magnetic spin quantum number. Now the radial part of an wave function of the wave function will depend upon the principal quantum number, and the azimuthal quantum number will depend upon n and l, and the angular part will depend upon l and ml. Now for p orbital, let's say for 2p orbital, so here n equal to 2, principal quantum number n equal to 2. Now the possible values, now for any p orbital, now the l will be equal to 1. So the azimuthal quantum number l equal to 1 means it is p orbital, and azimuthal quantum number l equal to 0 means it is s orbital, and l equal to 2 means it is d orbital, l equal to 3 means it is f orbital. Now for 2p orbital, n equal to 2 and l equal to 1. Now possible values of ml are minus l to plus l. That means here in this case the possible values of ml are minus 1, 2 plus 1. That means minus 1, 0 and plus 1. For p orbital, the possible values, there are 3 possible values of ml: minus 1, 0 and plus 1. Now for let's say for 2pz orbital, let's say for pz orbital, the angular part theta phi is just cos theta times e to the power I ml phi for any p orbital. Okay. For pz orbital, the angular part will be cos theta times e to the power I ml phi. Now for pz orbital, let's say ml equal to 0. ml equal to 0, that means for y theta, the angular part for pz orbital will be just cos theta. Now for p, now this is for p0, that means we denote p orbital as 3 ml values, right? So p minus 1, p0 and p plus 1. Now pz orbital is actually p0. That's why we put ml equal to 0, so it will be just cos theta. Now for p minus 1, it will be just sin theta times e to the power I ml phi, which will be the ml equal to minus 1 in this case, so sin theta times e to the power minus I phi. Now for p plus 1, it will be sin theta e to the power I ml phi, which will be equal to sin theta e to the power plus I phi. Okay, so now we know the how do we extract the ml value from a angular part of the wave function. We operate minus I h bar del phi. Now for any this is actually the angular the LZ operator, that means the angular momentum quantum operator. So not the LZ operator, actually, yeah, LZ, Z component of the angular momentum operator. Yeah, so just by looking at this angular part, like for pz orbital, the e to the power I ml phi, from this part we can, by looking at this part, the phi part, we can extract the ml value. So in this case there is no phi part, that means the ml equal to 0. Now for this p minus 1 angular part, the phi, if you just look the phi part, so there is minus sign here, so the ml equal to minus 1, and in this case ml equal to plus 1. Now the px orbital can be constructed by the linear combination of these two orbitals, p minus 1 and p plus 1. So if you just look at this, pz orbital is just the cos theta, right? So this is actually real. So by varying theta, you can plot the pz orbital. But p minus 1 and p plus 1 orbital has the complex part. This I is the complex quantity. That means I equal to root over of minus 1. So you cannot plot this p minus 1 and p plus 1 function on a paper or on a three-dimensional software, in a software. So you cannot plot this complex wave function. So to visualize the wave function, our px and py wave function, we have to take the linear combination of these two wave function, p minus 1 and p plus 1. So px orbital can be constructed by the linear the plus combination of p minus 1 and p plus 1. That means p minus 1 plus p plus 1. So sin theta e to the power minus I phi plus e to the power plus I phi. divided by 2. So sine theta, so this combination will be cos phi, right? So we know the e to the power Euler's rule, e to the power I phi equal to cos phi plus I sin phi. So if you just take this combination, e to the power minus I phi plus e to the power I phi divided by 2, it will be equal to cos phi minus I sin phi plus cos phi plus I sin phi divided by 2. Okay, yeah, just checking the net, divided by 2, which will be equal to cos phi. So px will be just plus combination of p minus 1 and p plus 1 wave function, and the angular part is sin theta cos phi. Similarly, py can be constructed as half of p minus 1 minus of p plus 1 divided by 2y, 1 upon 2y. So it will be just sin theta sin phi, p plus 1 p minus 1, sin theta sin phi, py orbital will be. Now the p0 or p minus 1 or p plus 1 has the form of just e to the power I ml phi, the phi part. I am just writing the phi part here. Now by looking at the phi part, you can tell the value of ml. Like for p0 case, there will be no phi part because ml equal to 0. P minus 1 case, it will be just e to the power minus I phi, and p plus 1 case, it will be e to the power I phi. But pz orbital is actually p0 orbital, but px, so pz orbital is basically p0 orbital. Px is a linear combination of p minus 1 and p plus 1, right? And similarly, py is also a linear combination of p minus 1 and p plus 1 orbital. So for pz case, you can tell the value of ml, that is ml equal to 0. But for px and py case, you cannot define a magnetic quantum number, orbital quantum number ml here, because it is a plus and minus linear combination of p minus 1 and p plus 1 for px and py case. So that's why you cannot define the ml value in this case. So that's why in this question, the value of magnetic quantum number of a px orbital, so that means px orbital is a combination of p minus 1 and p plus 1 orbital. So that's why you cannot tell the ml value here. So in this case, the question in the answer will be option D, undefined. Now if it was asked that the magnetic quantum number of a p minus 1 or p plus 1 orbital, you can tell the exact value of ml value, that is minus 1 and plus 1. But for px and py orbital, you cannot define the ml value because it is a plus and minus combination of these two functions. Okay, so option D is the correct answer in this case. Okay, any doubt from this question, or it is clear?
Yes, sir. Yes.
Okay, great. Okay, just a second. So this is question number 11 from the same 2014 paper. The question says the number of SS bonds in H2S5O6. So this is actually pretty simple. So if we just draw the structure of H2S5O6, that means S double bond O, so this is the structure of H2S5O6. So the number of SS bonds means, so there will be just, this is one SS bond, 2, 3. No, H2S5, 1, 2, 3, 4. Oh, okay. So in this case, there will be just 4 SS bonds. Now in general, for any H2S, in general H2SN O6 case, the number of SS bond will be just n minus 1. In general, for this type of molecules, the number of SS bond will be just n minus 1. Why? Because these two structure will be the same, and in the middle the S bond, the S atom will increase. So in general, for H2SnO6, the number of SS bond will be just n minus 1. So here in this case the answer is 4. Okay, so now let's just move to the next question. Okay, so this is question number 33 from the 2014 paper, and the question says of the following plots, the correct representation of chemical potential against absolute temperature for a pure substance, solid, liquid and gas respectively. So the 4 options are given. We have to find out the correct representation of chemical potential versus absolute temperature. Okay, now so first start from the basics of thermodynamics. Like we know the Gibbs free energy G equal to H minus Ts, right? So H is the Helmholtz free energy, T is the absolute temperature, and S is the entropy. So G is the free energy, Gibbs free energy, H equal to Helmholtz, T is the temperature, and S is the entropy. Okay, now so H equal to, we know the U plus Pp, where U is the internal energy, P is the pressure, and V is the volume. So in general, the G equal to U plus Pv minus Ts. Now we know the thermodynamic relation dG equal to minus HDT plus VdP plus mu dN, right? So this relationship is actually for one component in particle system. For one component in particle system. Now if we just differentiate with respect to n, like we know the chemical potential is is denoted by mu, which is gives free energy per particle. So that means del G del N, constant temperature and pressure. So this is the expression of chemical potential. Now if you just differentiate this expression with N, so del G del N at constant temperature and pressure means this term will be equal to 0, and so mu will be equal to just del G del N constant temperature and pressure. Now for one component, one particle system, so we know the chemical potential U equal to U plus PV minus Ts, but these are small u and small v like this. So similarly d mu will be equal to minus s dt, this will be s bar plus v bar dp like this. That means s by n and the v by n like this. So mu equal to g by n in general. So s bar will be s by n, v bar will be v by n like this. Now if you just differentiate with respect to temperature here in this, from this equation, del mu del T, so it will get minus of s bar, right, constant pressure. And if you just differentiate mu with respect to pressure at constant temperature, you will get v bar. So you will call this our Maxwell relation, right, thermodynamic relation. Now so del mu del T basically minus of s bar, minus of s basically entropy, negative of entropy value, negative of absolute entropy. Now del mu del T means if you just plot mu versus temperature, so del mu del T will be just slope. Let's say this is random plot. So del mu del T is basically slope of this plot, right, del mu del T. So slope of this plot, so slope of mu versus T plot is basically negative of the absolute entropy, minus of s bar. You have to just remember this. Now what is entropy? So entropy actually the measure of randomness or the measure of uncertainty in a system. So it is actually measure of randomness or uncertainty in a system. So if a system is more disordered or random, the entropy value of that corresponding system will be higher compared to a ordered system or ordered arrangement. So by the value of entropy we can figure out how random or how disordered our system is. So it is actually measure of randomness. For a gaseous system, so gas particles generally move at a particular temperature randomly, right? So there are no proper or ordered arrangements between the gas particles in a gaseous system. They move randomly. So that's why the entropy value for a gaseous system is generally higher. And for liquid system, if we just draw, so gas particles moves randomly, and for liquid system you can see a short range order and long range disorder. That means, let's say this is a particular molecule, water molecule. Let's say this is liquid water and this is a particular water molecule. Now if you just concentrate on this water molecule in the liquid water system, you can see for there is a different solvation cell, right? The first solvation cell, second solvation cell, so that will be there. That means just this water molecule, another water molecule will be hydrogen bonded like this. So basically there will be a first solvation cell around the center water molecule, and there will be also second solvation cell also. So this is actually first solvation cell, this is second solvation shell. So basically around the center water molecule there is a short range order. Why short range? Because this order actually persists in a very short, up to very short range around the center water molecule. So in the liquid system there is a short range order, and long range there will be again disorder, because there will be no proper structure in the liquid system. So due to this short range order, and in the liquid the intermolecular interaction is even higher compared to a gaseous system, so that's why the entropy value in this case is lower compared to the gaseous system. And in solid, there is a periodic arrangement. In crystal there is a periodic arrangement of atoms, so the solid is completely ordered arrangement, so that's why the entropy value of the solid is lowest. So S entropy value for gaseous system is higher than the liquid, than the solid system. Now we have seen that the del mu del T at constant P, that means slope of the mu versus T plot is S bar, that means minus of S bar, that means negative of the entropy value. So del mu del T will be highest for solid case, then the liquid, then gas, because it is negative of the entropy. Now if you just look at the plots here, it is mu versus T diagram. Now the first plot, the solid is higher, like the entropy, so actually for solid is higher, then solid is higher, then the liquid, then the gaseous. So actually from this plot, the del mu del T is higher in option A for the solid case, and then the liquid, then the liquid, then the gaseous system. Then option B is completely opposite here. So del mu del T is lower, then in solid, then liquid, then gas. And C or D is different behavior, solid, liquid and gas, and the solid, liquid and gas. So in this case, so for different phases, the mu versus T diagram will be just option A. First there is solid, then liquid, then the gaseous system, because entropy value, so del mu del T is basically minus of negative entropy value, so that's why the mu versus T diagram will look like option A. So here in this question, the option A is the right answer. Okay, so any doubts from this question?
No, sir.
Okay. Okay, so you guys have any specific doubts today? for any particular topics or apart from questions also? No? Okay. Okay, great. Okay, great. Then I think we'll meet in the next week, because also I'm not feeling well today. So everything was clear now from this class? Okay, thanks. Okay, so we'll meet in the next week. Okay. Bye. I'm just ending the session today. We'll meet in the next week and we'll solve again 4 or 5 questions. Thanks for joining.